Welcome to Real Chemistry. Today we're going to talk about something called heats of formation. And heats of formation is a special type of enthalpy. If you're not familiar with enthalpy, I recommend you go ahead and watch my video, Enthalpy and Stoichiometry, first. That'll give you a better frame of reference to understand this video. What we're going to do here is I'm just going to introduce what enthalpy of formation or heats of formation are, and then in my next video we're going to use them to do calculations and solve chemical problems. Enthalpy of formations are a tool to calculate enthalpies of reaction. What's the difference between those two things? Well, you can see down here below that there's two chemical reactions. One of them has a delta H RXN, that's an enthalpy of reaction, and one of them has a delta HF, that's an enthalpy of formation. Now you might look at those and say, why in the world are we using two different symbols to talk about enthalpy for these two different reactions? Well, the reason is that the bottom reaction is forming a compound from pure substances. So we combine sulfur, which is just sulfur by itself, that's a pure substance, and oxygen, that's pure oxygen by itself, to make sulfur dioxide. So whenever you combine pure substances to make a compound, that's called an enthalpy of formation. And that's different from what we see above, where we see CH4 combining with oxygen. CH4 is methane, and it's not a pure substance. It's a mixture of carbon and hydrogen. So that's the reason they're different. And what you'll find, if you look in the back of your chemistry textbook, is a giant table that'll tell you what the enthalpies of formations are for different compounds. So right next to sulfur dioxide, it'll say the enthalpy of formation is negative 297 kilojoules per mole. What that means is, if I form sulfur dioxide from pure substances, it will give off 297 kilojoules for every mole I form. So that's why we use different symbols. One of them is for forming a compound from pure substance. And the other is just the enthalpy of a reaction regardless of what those reactants or products are. And remember, the whole goal of heats of formation, which we'll accomplish in the next video, is as a tool to go from the enthalpy of formation to the enthalpy of a reaction. So we'll use it as a tool to calculate the enthalpy of a reaction, that is the heat absorbed or released by a reaction, even if we've never run that reaction before. So you can predict, if you're going to go into the lab and run a brand new reaction, you can use enthalpies of formation to predict how much heat will be released or absorbed by that reaction, and that's why they're powerful tools. We're going to go through the definition of enthalpies of formation in a little more detail. They turn out to be relatively technical, so stick with me, try to understand these enthalpies of formation, and then watch that video where we're going to use them, and I think you'll have a better understanding of this topic. So, I've already said that heats of formation are the energy needed to form a substance from, to form a compound from pure substances. And particularly, it's 1 mole of that compound. So it's not just, 2 grams or 10 moles, it's 1 mole exactly. And that's why in the previous reaction, we saw that we were forming 1 mole of sulfur dioxide, so there was a 1 in front of that. Similarly, if we want to look at the enthalpy of formation for NH3, that is ammonia, down here, there's a 1 in front of that. And what that means is we're looking at the enthalpy for that reaction, that is forming ammonia, when we're forming just 1 mole. And that's why you see these weird fractions, which you don't usually see. You see 1/2 nitrogen and 3/2 hydrogens. And the reason they use half numbers is to make sure we only make 1 ammonia. So if this reaction was correctly balanced, it would say you combine 1 nitrogen and 3 hydrogens to make 2 ammonias. But then it wouldn't fit the definition of enthalpy of formation, because the enthalpy of formation is for exactly 1 mole. And that's why you see these halves here. So those function as a tool to make the enthalpy of formation more useful to be able to calculate enthalpies of formation. Okay, let's talk a little bit more about enthalpies of formations. If you go into your textbook, like I've mentioned, you'll find a table. You won't see a bunch of these reactions that I've been showing you. They're related to the definition of an enthalpy of formation, but this table is what you'll see in the back of your textbook. And you'll see that, if I make solid water, that has an enthalpy of formation of negative 890 kilojoules per mole. And what that means is if I formed water from pure hydrogen and oxygen, and it formed solid water, that is ice, it would give off 890 kilojoules for every mole I formed. And so in practice, you don't really have to worry about the reactions you're going to run to form that water. You're just going to look up in a table, hey, there's water, and there's this 890 kilojoules thing next to it. Now, notice here that the phase matters. So if we're going to form liquid water from pure substances, that gives off a different amount of energy. Why? Because liquid and solid water is just different. So, one last thing to notice here. Towards the bottom of the table, I have some pure substances. Silver, nitrogen, oxygen, you notice that all the pure substances have enthalpies of formations of 0. And that has to be true by definition because we're forming our compounds from pure substances. So what's the energy it takes to make pure silver from pure silver? Nothing. And that's why it's 0. I'll show you a little more clearly what I mean by that in the next slide. Okay, one last technical detail. These tables are made for reactions run at 1 atm and 25 degrees Celsius. If you change the temperature or pressure a reactions run at, you'll slightly change the enthalpy. And so when we want to create these giant tables, all the scientists have to get together and agree, okay, we're going to run them at these fixed circumstances so that we can compare our data effectively. And that's why we run them at what we call standard state. And that's actually why you see this degree sign up here. Whenever you see that degree sign by some thermodynamic variable, that means it's for standard state. It's for being run at 1 atm of pressure and 25 degrees Celsius. All right, let me talk a little bit more about why heats of formation for pure substances are 0. So let's say we want to form nitrogen, N2, from pure substances. What reaction would that be? Well, what we do is we need to start out with the pure substance that is nitrogen, which is N2. And then we need to go ahead and take that to N2. And that reaction would give us the enthalpy of formation for nitrogen. But guess what? How much energy does it take to form nitrogen gas from nitrogen gas? 0. And that's why the delta H at standard state for forming nitrogen is equal to 0. So heats of formation for pure substances are 0. And that's actually really important when you go to do calculations. So this has just been an introduction to what enthalpies of formation are. And you can see why I didn't stick it at the front of the other video. It would be difficult to watch this and then do the calculations. It's much nicer to have this clear separation. So this is what an enthalpy of formation is. It's a tool to calculate the enthalpy of reaction. And I'm going to show you how to use that tool in the next video, calculating enthalpy of reaction from heats of formation. Thanks for watching this episode of Real Chemistry. If you have any further questions about enthalpy of formation, ask them below. Visit my channel to see a bunch of other chemistry videos, or subscribe to receive updates when I post new videos.